Hello and welcome to lecture 1 of this course on advanced plasticity of solid continuum. In this talk we will cover the basics of motion configurations, all embedded within the philosophy of the continuum models for solids. So let us start. So the first question comes up as to why we should study continuum plasticity at all in terms of the usefulness, etc. So you typically have large plastic deformations which are inevitable in manufacturing processes, or at least in many of them. For example, in metal forging, rolling, etc. So all modern manufacturing processes for components typically involve large plastic deformation. And if you have good continuum plasticity models, trustworthy models for plasticity, then you will be able to simulate and optimize the manufacturing process itself, and you will be able to do defect prediction so that you can optimize the manufacturing process to the best possible extent that you can never do by a trial and error method. Also, plastic design allows for lighter, safer and more effective structures, more efficient structures, because it utilizes material capacity beyond elasticity. So you have less factor of safety incorporated automatically in your design. And accurate plasticity models are essential for also predicting the fatigue life of components and damage accumulation and also failure. So the idea is therefore of all this is to go into the continuum model is to provide a rigorous bridge between what actually is the reality, which is a defect microstructure that evolves leading to plasticity, which is too complicated to handle, and a bridge that offers a connection between this evolving microstructure and the macroscopic structural performance. And that's where the continuum models come in. Here is a typical example of why in a manufacturing process of many components, large plastic deformation comes up. This is an example of forging, in which you see you have here on the left you have this component, and essentially what you do, you make this component undergo huge impact, right, enormous force which shrinks the width of this component, right, and you see in the process the component loses its elasticity and undergoes large plastic deformations, and in the process you have lots of different phenomena, these dislocations which are part of this defect microstructure that evolves, and you have recrystallization, a finer grain structure. These things we will be talking about as we go along. But what is important to understand here is that without making this particular component undergo large plastic deformation, you cannot make these thin sheets and things like that, right? So that's a very important thing to remember. So there are certain prerequisites which we need to really have you assimilate this course in the best possible manner. This includes basic linear algebra and vector and tensor calculus also, a basic MTech level course in elasticity or continuum mechanics of solids, and a basic understanding of the PDEs, partial differential equations, to the level as taught in the undergrad level, right. So if you have requirements for any one of these prerequisites, then you can look up the NPTEL lectures by others and get yourself up to date. Now let us talk about why we need continuum models at all. So especially given the fact that the physical solids are discrete at the microstructural, that is at the atomic scale, there is nothing continuous there. So the microstructural aspects include many of these defects. It has so typically metals have a lattice structure, but the atomic positions sometimes are not filled in. So you have dislocations, you have possible voids in the metallic component, you have inclusions, grain boundaries, etc. These are all part of the defect microstructure, defects, right? So if you want to model the whole thing, the entire microstructure, you will have to end up dealing with about billions or trillions of degrees of freedom, which will be difficult, if not impossible, to do for large components, right? Even with all the facilities on advanced computing that we have these days. So what we need to do is to average out these microscopic things, arrive at appropriate macroscopically describable, features or variables that can still capture the experimentally observed plastic response of solids. So that's exactly where continuum mechanics comes in. It provides a smooth and drastically dimensionally reduced description for the solid. So plasticity must track, therefore, both, unlike elasticity, which you may have already gone through in your earlier courses. Plasticity is not just about the deformation of the body. It is also about the microstructure, how the microstructure evolves. In fact, it co-evolves with the deformation. So it is quite unlike elasticity from this angle. So let us talk of a typical defect that is so important in metallic components when they undergo plasticity. These defects typically are called dislocations. On the left here, you see a typical lattice, basically all the atoms stacked together in a nice neat pile. Then on the right, on the middle rather, you have these green balls, which basically indicate the fact that there are no atoms there. In fact, this is a part of the defect. That means the atomic locations are not populated with atoms. These are the green balls that you can see here, right? So this is what dislocations are. And under loading, these dislocations, that is this positions which is not filled with atoms or occupied by atoms, they start moving under external loading. But we cannot track the motion of each such dislocation, because as I said, that will lead to a huge number of degrees of freedom which we cannot handle. So the continuum body on the right gives an averaged, macroscopically averaged description of this kind of microscopic motion using functions which are perfectly smooth and using sets. All you see here is a set, right? This is a set consisting of points which are the number of such points which are the material points, they are infinite. So this set is a continuous set. So in continuum mechanics, you use smooth descriptors, smooth variables which are differentiable any number of times that you need, and you use sets which are continuous, right? So these are the two important things to remember. So let us talk of, from this point of view, a material body which is an abstraction in describing the continuum. So a material body is typically modeled, call this material body as script B here, right? It is typically modeled as a collection of material points. Each such point represents a small but finite neighborhood. If you zoom deep inside, a point doesn't have any volume, right? But here, if you zoom deep inside, it is as if the point expands and reveals before you the microscopic structure, the atoms, the presence of dislocations and other defects and things like that, right? So essentially, when you talk of a material point, we also talk of we are also interested in a small if infinitesimal or finite neighborhood about this point. Right. So, this leads to a dimensional reduction. For example, instead of about 10 to the power 23 particles in the actual microscopic 3D domain, you will have just about hundreds or thousands of degrees of freedom. That sort of a reduction. You describe appropriate fields. These fields could be stress, strain, temperature, things like that. Deformation also. They are defined smoothly, and what is very important is that this abstraction enables you to write the governing equations in terms of partial differential equations, for which we have very good tools like the finite element method for discretization and numerical solution. Right. So, this is the overall setup. Right. So, remember that the continuous set of points that we were talking about in the previous slide is encapsulated in the form of the set B, script B. All right. So, as I was saying that every material point, here is a material point, right, and every material point should be looked upon as a small volume in the microscopic level, representing a representative volume element for the microstructure. So, if you zoom it, you will be seeing something what is shown here, that is a lot of atoms, some missing positions, dislocations and things like that, many other defects, right. So, in that sense, every material point is a representative of a representative volume element in the microstructure, right. Now, we are now ready to talk about the configurations and motion as smooth descriptors of the deforming solid. So, basically when we talked of the material body here, right, the material body, or even here, right, the material body, this is the material point. I just talked of a set of points, I did not talk of their coordinates. So, a material body is just a set of points without a reference to what your coordinate system is, right. But we have to now assign appropriate coordinates to this material, to these points, right. So, herein comes the notion of a reference configuration. A reference configuration is all about a material body itself, perhaps, or a transformation of the material body. Typically, we talk of an identity transformation, that is, let the material body itself denote the reference configuration, but with the additional caveat that you now describe each material point with an appropriate coordinate system, maybe a Cartesian coordinate system or something else, and call this reference configuration as omega 0, right. Now, as you apply the external agency, which is in the form of external forces or temperature or whatever, or even electromagnetic excitations, then you actually observe the body to change its shape, it deforms, and what is even more important in the context of plasticity is that the microstructure starts evolving simultaneously. So, all these you describe using a time parametrized collection of configurations, which we call omega t here, okay, the parameter being time. So, for each such fixed parameter t, you get a configuration, which is called this current or spatial configuration. It is also called the spatial configuration. So, let me tell this again. In brief, we have a reference configuration omega 0, which we fix appropriately based on my material body with coordinates describing each point, and a current configuration which is not just one, but a collection, infinite collection parameterized by time, right. And then the motion, which is call it xt, it is also parameterized by time because the set itself is parameterized by time. This motion is given in terms of the coordinates of the reference configuration and time by the function phi here, right. So, the function phi is again time parameterized, and it is also a function of the coordinates of the reference configuration. We call these coordinates with capital X. The result, the image of this function, as you can see, is another coordinate small x, but it lives in the current or the spatial configuration, alright. So, the important thing here is that phi is a smooth map. That means you can differentiate it as many times as you wish. It is an injective map. So, if this is your omega 0 and this is your phi, we also write phi xt as phi t of x, right, and then we get the deformed or the spatial configuration at time t. You see, if you take a few points here in the material body or in the reference configuration, you get as the image of phi the corresponding, for this you get a point, it is the image under phi, it is the displaced point or the deformed point. You get another here, right, corresponding to each one of these you get 1 point, right. The important thing is that this mapping is bijective, that is, actually it is injective, but it is also a bijective map, in the sense that corresponding to each such image crosses in the deformed configuration, you have a unique pre-image, a material point in the undeformed on the reference configuration. So, there is one more important thing, no two so there is a uniqueness, right. So, corresponding to each such cross there is a unique dot. So, corresponding to each such dot there is a unique cross, both are true. In other words, corresponding to two different dots in the material body or the reference configuration, you cannot have a single cross. That means 2 points cannot merge into one, right. In other words, I can say that the mapping phi is invertible. You can invert it to get information about the material body, right. So you can understand that phi therefore maps material points to the spatial positions. And so typically we identify this omega 0 when there is no stresses or external agency put on the body. That means it is undeformed, right, typically. It is not necessarily so, but typically that is the case. Now we move on. So, we have the reference configuration. These configurations, some authors also call these configurations as placements, right. The word placement comes from the fact that these are all coordinatized, right. Each point has as its identity a coordinate. Alright, so we have this reference configuration omega 0 under the mapping phi, which is the deformation map, under some externally applied loading of some kind. You have the deformed configuration for a fixed t, it is called omega t, right. As I said, the deformation map is injective or rather bijective and smooth in both the arguments, that is in both capital X and t. T is here the time, okay. So, now you probably understand that the deformation map establishes a one-to-one relation between the material and spatial descriptions. Most of you who are aware of the basics of continuum mechanics may be knowing this already. Now, injectivity ensures, as I said, that two different material points can never merge post deformation. Now, think of a collection of points which are given by subsets of the material body or the reference configuration omega 0. So, let P be a proper subset of omega 0, call it a material region. Now, you can think of the deformation phi such that it convects this subset P to get a new subset PT in the deformed configuration. How do you get this new subset? You apply the map phi t on P, on the subset P, and get PT. For every t you will be getting a new subset in the deformed or the spatial configuration. The important thing is here is that the boundary of this subset P, which we call as del P here, right. This is the boundary of the subset P. If this is my subset, this is my undeformed configuration omega 0, and this is my P, right. This is my boundary del P, all right. So this boundary also gets mapped by phi t, the parametrized map, time parametrized map phi t to del pt to the deformed configuration. There is no space here, so I will draw the deformed configuration here. This is my deformed configuration omega t. This is how pt, this p mapped under phi t x looks like. So this is my pt, this is my del pt, right. So the important thing here is that no material can cross this del pt. If it were to cross this del pt under the mapping phi, then the injectivity, this 1-to-1 correspondence would be lost. Think about it, you see. So therefore the material cannot cross from here to here under the mapping phi, all right. This is not allowed. Okay. Now also we often talk of displacement, right, but there is a problem always in talking of displacement in a properly mathematical manner. You see, we may define displacement of a point, right. It is as if the point which was originally capital X goes to small x, and so the displacement is given by small x minus capital X, but we already know that small x is phi, right. So this is nothing but small x, the coordinate in the deformed configuration, small x t, correct. So you can define u of x comma t, the displacement, as the distance or the difference between these two vectors, these position vectors of this deformed point x t minus the original referential point capital X. But in doing so, you assume that the deformed body and the undeformed body omega 0, they constitute the same geometric space, which may not be true. In fact, reference and current configurations are distinct sets, which is fine, but if there are no defects like in elasticity, these two distinct sets are trivially isomorphic. They are 1-to-1 relatable, right, through the deformation. But in defective solids, this is no longer the case. That means these distinct sets are so different. The set in the undeformed body and the corresponding set in the deformed body are so different that a trivial isomorphism between the two may not be possible, right. So in this situation, that means if there are defects which are also undergoing motion in the process of deforming the body, then the notion of displacement becomes very difficult, because you cannot directly subtract small x from capital X. It is not that easy, because you do not even know if you are subtracting it from within the same or equivalent sets, right. That is the problem. So if you identify these sets properly, and if you are sure that they are trivially isomorphic, it is only then that the displacement is meaningful, right. Otherwise, what actually is meaningful in mechanics of solids is essentially the deformation gradient, which is the gradient of the phi, the deformation map with respect to capital X, the position vector in the undeformed configuration. This is called the deformation gradient. So that is a very important quantity that we deal with, because straining of the body is related to this deformation gradient. As I was telling you, let me just stick with this point a little more, because this is a very important point and very few authors talk about it, very few people talk about it, very few instructors talk about it. So this is an Euclidean body. An Euclidean body is basically a set of points, like all these points, plus the Euclidean distance is incorporated in describing this body. That means the distance between this point and this point is basically this Euclidean standard distance, right, which you actually can find based on simple vector analysis. That means if this is y and this is x, then the Euclidean distance is the usual way that you find the distances. On the other hand, if the deformed body loses its Euclideanity, that means the distance between points is not that simple. Suppose you try to measure the distance between this point and this point in the deformed body. Then you see, if there are defects like inclusions or voids, or dislocations, this is the typical way that you talk of you write, you denote dislocations, okay, like an inverted T. These are edge dislocations. This is not a material science course, so I will not be going into the details of what are dislocations and all that. There are other types of dislocations as well. This is a continuum version of the whole defect microstructure, so therefore we need not get into the details of the material science aspects. But what is important to understand is that in between these 2 points, crosses, in the deformed configuration, there are, when you try to measure the distance, there are objects which are sitting, like these voids or these cracks or these dislocations or inclusions perhaps, right. So the measurement of distance is not that simple. So that is why we can say that this body is non-Euclidean. This body on the right is non-Euclidean. This body is non-Euclidean, right. So a non-Euclidean body, unlike, so in an Euclidean body, if there are 2 tangent spaces, they are related by a path independent isomorphism. The isomorphism between the tangent spaces at x and the tangent space at y is not path dependent, okay. That means it is not dependent on how you connect these 2 points, whether by a straight line or by a curve and all that. But in a non-Euclidean body, like a Riemannian body like this, any 2 tangent spaces, tangent space, right, a local descriptor of what is happening just in the infinitesimal neighborhood of a point, right. So any 2 tangent spaces are not relatable by a path independent isomorphism. Here the relationship between these tangent spaces will depend on the path by which you go from this cross to this cross, right. So that is a very major difference. What is even more important is that in such cases a defective solid like this may not be even embeddable in the 3-dimensional Euclidean space. You may need a higher dimensional Euclidean space to embed this body, right. So all that I am trying to say here is that the actual mechanics, if you wish to use this kind of descriptors, geometric descriptors for this, it becomes very complicated. Mathematics is quite non-trivial for this. So we do not do that, but it is better to remember this given the fact that we use the word displacement so carelessly. So that is not to be used that way, because this displacement per se for this kind of solids has to be properly qualified before quantification, right. It is not quite obvious what displacement is for such solids, right. So now we were talking about the deformation gradient, this is just a recap of basics of continuum mechanics. So we were also talking of the tangent planes, tangent space about a point. So here is the dot which is in the reference configuration here. This is that particular point, material point in the reference configuration. Think of a tangent space containing this material point, the tangent space corresponding to this material point. Even though I am showing it as a kind of a square, it is not. First of all, please understand that this is a 3D object, so a tangent space typically would be more like a cube than a square, but anyway, for the sake of explanation and convenience, expositional convenience, I am writing it this way. So this tangent space, as I said, talks about what happens in the infinitesimal neighborhood of this point, which is circled, right? And therefore we can talk of the other points which are in the infinitesimal neighborhood of this. So therefore we can talk of such points by denoting by dx the infinitesimal distance or the infinitesimal vectors that are directed this way or this way. Dx can be directed in any way. They basically live on this tangent space. Truly speaking, dx is not a vector, a covector. It is actually a covector, but we do not get into these distinctions here because this is a more elementary course on plasticity, right. So you see, so basically therefore the neighborhood of the point capital X, the material point capital X, is described by all such infinitesimal vectors d capital X. And the relationship between, so this d capital X under the deformation map phi becomes another vector in the deformed body. This is my small x, this is actually small x, right. So this is the map of capital X, this is my capital X, this is the small x, this is the map of capital X under phi, and the map of dx to this d small x to a small arrow like vector like object describing the infinitesimal neighborhood of this deformed point small x is captured by this deformation gradient. That means if you multiply the deformation gradient with the vector d capital X, then you get the vector d small x, right. So in other words, this also implies that this follows directly from this definition, right, that f is basically the deformation gradient, that is the gradient with respect to capital X of the deformation map phi. Now sometimes in mechanics we use multiple symbols for the same thing, that is the typical thing that happens, because many authors have contributed to it and many symbols have come into force and all of them are used at some time or the other. So another way of writing f is by capital GRAD, grad of phi, right. When we say capital G here in grad, then it means that the gradient is taken with respect to capital X, that is with respect to the coordinates of the undeformed configuration omega 0, right. So we already have seen that this is true. So if you think of d capital X as a small line element in the material body, right, infinitesimal line element, then the corresponding image of it under phi is given by f, is actually the image is given by f dx, so which is d small x, right. This f, the important thing is that as I was talking of tangent spaces, in the previous slide if you go, this is a tangent space, this is the corresponding tangent space for the small x point in the deformed body. So essentially f is carrying information from this tangent space in the material body or the undeformed configuration to this tangent space in the deformed body. Well, so this is essentially what f is doing. So f is the carrier of infinitesimal information about the length, but also about the not just length but also about the angle, right. So basically f encodes within itself, because as you can see here, this dx, d small x here need not be collinear with d capital X, right. It may have rotated in the process of deformation, right. So basically capital F, the deformation map, captures both stretch and rotation. One important thing that directly comes from the fact that no two material points under the image phi become a single deformed point. That means the volume, if you just map a volume under phi any volume, even a small volume in the undeformed body, if you track how it deforms under phi, then that volume can never go to 0. Okay? This is a very important thing in mechanics of solids, and we capture this by requiring that the determinant of F is greater than 0. If you recall the definition of determinant, if this is the undeformed body omega 0, right. So, any point capital X, you have this tangent space which is spanned, you should remember your basics of vector algebra, by E1, E2, E3, 3 vectors, right. Let us say they are orthonormal and they are of unit length, right, unit vectors. So, they are mapped by these 3 vectors. So, now F will act on each one of these 3 vectors, right. So, F E1, the vector, F can act on a vector, right, it will become the vector E1 in the deformed configuration. Similarly, F E2 will become E2 in the deformed configuration, and so on. F E3 will become small e3. And then what does determinant F do? This determinant F is nothing but the F E1 cross F E2 dot F E3 divided by E1 cross E2 dot E3, correct. That is the definition of determinant of a matrix, So, basically what the numerator here tells you is that it is the volume enclosed by these small vectors E1, E2 and small e1, small e2 and small e3, whereas this volume is enclosed by this capital E1, capital E2 and capital E3, which is 1 in this case, right. This is the vector, this is the scalar triple product, right. So, this is the definition. So, you can see that basically we are talking of j greater than 0. When we talk of determinant of F equal to j greater than 0, we talk of the volume change, and this volume change can never be degenerate, right, because the volume can never go from non-zero to 0 under the deformation. So, this F is the foundational quantity for defining strains. So, deformation is not the main thing, it is the deformation gradient that is the main thing, because it is related to those PDEs that we will be defining soon to describe the solids, the rules of motion of solids, right. The PDEs work only in the tangent space. All the quantities in the PDEs are tangent space objects. They have no finiteness associated with that. For example, dy by dx, when you write, it is basically a tangent space object, right. Unless you integrate them, there is no finiteness associated with I mean, there is no direct interpretation of these terms in terms of experimental evidence, right. Only when you integrate a PDE, you will be getting something that you can measure in an experiment, right, not before that. So, that is why F, this which transforms the one tangent space to another, is a very important object. One specific case for this F is, you can understand that F is a 3 by 3 matrix, right. It is a field of matrices essentially, being a function of capital X and T. If F is constant, think of it to be a constant matrix, then we call the deformation to be homogeneous. In that case, if y and x are 2 material points separated in the material body or the undeformed configuration omega 0, then phi y and phi x are the corresponding deformed points. So, phi y will be the small y, phi y is basically small y, and phi x is basically small x. So, this y minus small x is nothing but, because f is constant, so f times capital Y minus capital X. This is obvious because f is the first derivative. So, if you do a Taylor's expansion of phi, right, about x, then what do you get? Phi y equal to phi x plus the derivative of phi with respect to x, which is f, which is a constant here, times, this times means here matrix vector multiplication. F is a matrix, this is a vector, and therefore you get a matrix vector multiplication, and you get the quantity y minus x in the process. Okay. So, but if you talk in a more general setting, then phi y minus phi x, if f is a function of x, then there will be other quantities that will be coming in the remainder, which will be order y minus x, small order. That means this will be higher than the quantity y minus, in terms of the order, this will go to 0 faster, this quantity will go to 0 faster, this is a small order. In terms of capital order, this is the modulus of y minus x square, right. So, this goes to 0 faster than modulus of y minus x does, all right. So, now if it turns out that G, think of G to be a matrix field, we also call it a tensor field that maps spatial vectors to spatial vectors, right. Then for example, so we can say that you basically apply G to one spatial vector, let us say G d small x, you will be getting something like dy, right, something like that, another spatial vector. Then because f maps material vectors to spatial vectors, we already saw that, didn't we. So, f transpose gf maps material vectors to material vectors. You see, G maps a spatial vector to a spatial vector, right, thinking of dx and dy to be vectors, as I said, with due apologies to mathematicians. Now then f transpose gf, let us see how it works. So, f maps a material vector to a spatial vector, that spatial vector is acted upon by G, leading to another spatial vector. F transpose, unlike f, is a mapping from the spatial vector to the material vector, right, the opposite, right, because it is a transport. So, finally, so f transpose acts on that spatial vector to produce a material vector. So, for this whole quantity, we have actually put a material vector and got as an output another material vector. So, this kind of operations are called pullback operations, right, pullback, that is the typical name, pull back, right. Right, and we can, instead of dx, we can also think of for example, in the spatial body or in the material body, this is my material body, right, this is my omega 0, instead of a single point here, I can think of a curve. The curve consists of a set of points, right, and you know that curve is parametrized by a scalar, call this scalar by tau. So, this is my curve x tau, correct. So, every point, for every tau you get a point, correct, and this curve in the material body is mapped to another curve small x tau, by under phi t x, this will be mapped to another curve small x tau, correct, under this 1-to-1 mapping. Now, if you take the derivative of this curve small x tau with respect to tau, which is d tau is nothing but the arc length, infinitesimal arc length, then you can simply say that dx tau by d tau is nothing but f at x tau dx d capital X tau by d tau. This is obvious from the very definition of your deformation gradient. Now, it may turn out that deformation map can be a rigid body motion, right. Rigid body motion is also a valid motion even though it produces no strain. What is a rigid body motion? So, the distance between 2 points in the material body and in the spatial body or the deformed body upon deformation will not change. So, this is the definition, right, you understand, the distance remains unchanged. So, no straining really. So, how do I express this rigid body motion? Recall that this phi, the deformation map in that case, will be written as q times t plus ct, where q is basically a proper orthogonal matrix which denotes rotation. You understand what is a proper orthogonal matrix, right, q transpose q equals identity and it is a proper orthogonal matrix. So, determinant of q has to be equal to +1, right. So, in such a case and ct is basically a translation vector, all right. So, basically therefore, you represent this phi as q the orthogonal matrix times x plus Ct, right. What is the deformation gradient in this case? It is just Qt, right. If you take the gradient with respect to capital X, then you just get f equal to Qt, which is a pure rotation. You can't differentiate Ct with respect to x because Ct, the translation, is not a function of x. We are not applying x dependent translation, nor are you applying x dependent rotation, right. Rotation is just a function of time, but not of the whole body is being rotated, right. Similarly, the whole body is being translated. So the rigid body motion produces zero strain and no stored elastic energy. That is true. We cannot have strain corresponding to rigid body motion, that is wrong, right, intuitively. So therefore, but F is Q in this case for rigid body motion. So F cannot really act as directly as a measure of strain, correct. So what acts as a measure of strain is something different then. Anyway, so we will come to that, but for the time being let us also quickly go through the notion of material time derivative and transport. So think of a material field, this is the function f, think of it to be a scalar valued function, it does not matter. If it is a vector function, you can take each component of it, which is a scalar. So therefore f is a function of capital X and t. So its material time derivative, which is called f dot, is the partial derivative of f with respect to t. You remember partial derivative, right. So there we hold x fixed, in, because that is the definition of partial derivative, right. So this is the definition of the material time derivative. But if instead of f we take a spatial field g, which is a function of now small x and t, then according to the formula for total time derivative and the chain rule, then we will be getting the derivative with respect to t of g, the total time derivative with respect to t of g, as we call it by capital dg by dt. Why it is called by capital dg by dt, I do not know. That is the typical, you know, symbol that we use in mechanics for a long time. So it has been practiced that way. So you know from basic calculus in real line or in Rn that this is nothing but del g by del t, if g is an explicit function of t, plus gradient of g. Now gradient with respect to what? This gradient is with respect to small x, right. So gradient of g with respect to small x dot by chain rule dx by dt, d small x, this v is nothing but dx by dt, right. So x dot. So therefore what you basically get is essentially, you know, this formula for the material time derivative of a spatial field gxt, correct. So this is also called the transport of, you know, because the formula for transport, because using velocity you basically track the motion of a point, right. So that is why it is this name. So now let us talk of quickly of the microstructure that is so important. As I said already that the microstructure of the evolution and the deformation co-evolve during plasticity. They have to be taken together, they have to be solved for together. So in order to, you know, define the microstructure at the continuum level, one very simple way is to define some smooth internal variables. They are called internal variables, just a name. It simply means that some aspects of the microstructure will be represented by these internal variables. Some examples of these will be plastic strain, which we will be coming across soon, and hardening variables. There is some phenomenon called plastic hardening, strain hardening. So those have to be represented by these hardening variables, right. So these are the internal variables that define the microstructure. Remember that the microstructure evolution is irreversible, so it produces dissipation, unlike elasticity where deformation is reversible. Microstructure evolution is not, and that is why you get permanent deformation in plasticity, right. So in elasticity deformation is reversible, but the microstructure is fixed, so you do not have to co-evolve microstructure with the deformation, but in plasticity you need to do that, right. and that is a very important point. This is exactly what the macroscopic signatures of plasticity would be. For example, if you plot some component of the stress, some shear stress versus some shear strain, right, based on an experiment on a sample which is undergoing plastic deformation, then you will typically see this kind of a scenario, right. You will be seeing some elastic part of the response, and then there is an yielding, initial yielding, call it sigma y0 on the stress axis, and then there will be a hardening like this, right, due to the evolution of the defects, and then evolution of the microstructure. And then what happens if you start unloading from here, you will be getting an elastic response, but we will never recover the full, the plastic strain will still be there here, right, in this region. And then you will actually see that the yield strength, which was originally sigma y0 here, has actually undergone a change which actually has increased, and it has become the same as the reflection of this point where from you unloaded on the other side, right, because you are now unloading, and then if this is in tension, then this will be in compression, right. You are actually going reducing the tension and then finally going into the compression side. Then that is what actually happens. So, all these details we will come to later on, but this is the typical case of the macroscopic signature of plasticity seen in the form of these irreversible hardening mechanisms. Right. So, the philosophical perspective for our whole work therefore is that the continuum theory is a scale separated description, is a very seriously scale separated. In defining these quantities like the internal variables, we do not always, in these internal variables, right, we do not always follow a proper homogenization of the microstructure to arrive at the internal variables. We just postulate often. If you are able to homogenize and arrive at these internal variables, then they will be physically much more transparent, but unfortunately our mechanics is not that advanced as to have a very clear, unambiguous description of such physically and geometrically transparent forms of internal variables. So, often we actually define these internal variables in an empirical manner, right. So, in the process we lose a lot of information on the microscopic detail, but hope to retain the structure. What structure? I will come to slowly about those. For example, the dissipation structure, certain aspects of convexity in the dissipation which ensures that it happens in a stable manner, right. These things, certain structure we need to incorporate in defining these internal variables, right. And yield surfaces. So, there are two kinds of plasticity that we will be discussing. One is a rate independent plasticity, which are typically encapsulated using the notion of what are called yield surfaces. So, here in rate independent plasticity, elasticity is already there and plasticity is considered as a constraint on the elastic response, and this constraint is provided by this yield surface, right. So, plasticity provides a force corresponding to this constraint defined by the yield surface, right. So, yield surface is the constraint, the stresses that produced by plastic deformation will be the corresponding reaction for this constraint, right. So, so you can think of rate independent plasticity as something like constrained elasticity, constrained by the yield surface, right. There is also rate dependent plasticity where the notion of yield surface as a specific constraint is not there, right. So, so it is not the empirical fitting from the experiment that guide us in our formulation. In this course, it is the structure that I defined, that I talked of just now, that will guide our formulation. The convexity aspects, the fact that just because there is a plastic deformation, the matter cannot fail just like that, right. The material does not undergo any failure, that sort of things. So, the thing is that the kinematic and balance laws will be the next things that we will be discussing. We will be basically talking of the after kinematics and the basic balance laws, which are derivable from Newton's laws, the local form of Newton's laws. We will be talking of thermodynamics, which is very important in defining the dissipation, right. we will be talking of the yield surfaces, but in this process we will be discussing convex analysis. We will be defining the yield surface using the language of convex analysis. We will be talking about associated flow rule and the variational structure associated with this evolution of the yield surface. Yield surface is a dynamic object, you know. So, we have a constraint which is a dynamic constraint in rate independent plasticity, right. We will be talking of the computational schemes and of course finite element implementation, so that you can simulate. So, the key takeaways from this lecture are as follows. So, first we have seen that the continuum body is an abstraction of discrete matter. It is an abstraction, but a very useful abstraction, because that sort of a computing power to actually solve for the entire discrete matter is not available with us. So, motion is a mapping, a smooth mapping between configurations or placements which have their coordinate based description of the points. Deformation gradient is the fundamental object, not displacement, neither is it deformation itself. It is the gradient that is the fundamental object that later on defines the straining, and from their stresses, and from there the governing PDEs, right. Plasticity requires tracking the microstructure, that is a very important point, and the mathematical structure will guide our theory, not any empirical scenarios. So, thank you very much for your attention.